another major part of motion is you considering motion with air resistance, specifically an object that falls with air resistance. So let's just consider a very simple case. Now, if I tell you you have, maybe I use a different color. If I consider a case where you have no air resistance, okay, this one is a case where I consider there's no air resistance. I go and drop an object. Okay, I go and draw an object, a ball, say for example. The only force acting on the object would just be the weight. And your acceleration here would actually just be equal to g. Okay. And then after that, what will happen is that your F net is actually equals to W. Your net force here is actually equals to W. And then after that, when your object drops, your weight doesn't change, right? Yeah. So F net equals to W, since weight remains constant, F net remains constant. Okay. So we also know that F net causes acceleration. So therefore, since F net is constant, A remains constant. A here refers to the acceleration. Okay. So now, based on these two statements that I just wrote, you understand that the weight remains constant. The weight itself is your resultant force, which in turn causes your acceleration. So since your weight remains constant, your net force remains constant, therefore your acceleration remains constant. This one, A equals to G, is constant throughout. Okay. Now, from here, earlier one of the things that I mentioned to you was that if your velocity is downwards and your acceleration is in the same direction, you will actually speed up, right? So the thing here is this: when you have no air resistance and then you just drop the object will actually speed up indefinitely. Okay, it will speed up indefinitely, or rather you can just think of it as continuously lah. Continuously continuously to infinity. Okay, it will actually speed up indefinitely. Speed up to infinity indefinitely means continuously to infinity. Okay, so it will just speed up as long as there's room for the object to fall. It will just keep on speeding up until it hits the ground. So if I talk to you about the velocity time graph of that object, if I try to draw for you the velocity time graph of that object, it will actually look something like this. Okay. And then if I try to draw for you the acceleration time graph of the same set object, it will actually look like this. Okay, so now, how do you know that the acceleration time graph would actually be a constant horizontal line that is positive?
Your sign convention.
Yeah, it's something to do with your sign convention again, because your sign convention is downwards positive, because your initial motion is downwards. So I can actually say that downwards is positive. So my acceleration is downwards. with respect to my sign convention, it will be positive. And because I already say it's constant throughout, the acceleration is constant and positive, no? Okay. And also from what I just mentioned to you, that acceleration is rate of change of velocity, where we mentioned that the value of acceleration is equals to the gradient of my velocity time graph. Because my acceleration value is constant and positive, my velocity time graph gradient will be constant and positive too. And this one, you see, is showing to you that my velocity keeps increasing, consistent with what I just mentioned to you here. Your object speeds up continuously. Okay, so this is one thing. And then the other thing that I can draw for you last is this one. What about the displacement time graph of the object? The displacement time graph of the object will just be a curve like this. Okay, it will just be a curve like this. It's actually kind of like half of a quadratic curve lah. All right.
This tree graph is when there's no air resistance,
Yes,
right?
correct. No air resistance. All right. For the displacement time graph, this one I know is because V is equals to rate of change of displacement, where value of V is equals to the gradient of my ST graph. Okay. So you see, this graph is the ones for an object falling without air resistance. Okay. So the graphs that you draw here are actually quite similar to what you drew in the previous examples. Okay. So this one is what you're seeing here for an object that drops without air resistance. Now, with air resistance, things become a bit different. Okay. So this is the main thing about your current subchapter. Now, with air resistance, if let's just say you have with air resistance, you have that same object that you are trying to drop down. Okay. So we consider a few different stages of its motion. Okay, initially we drop the object from rest. You have weight W. Okay, yeah, just to recap a little, the forces density pressure chapter, last time I mentioned to you, air resistance is something called viscous drag or drag force, right? So the thing that we needed to remember about air resistance is mainly just two main things. Air resistance always opposes motion. Air resistance always opposes motion. And then air resistance is directly proportional to speed. So meaning to say, when your speed increase, your air resistance increase. Your speed drop, your air resistance drops. If your speed is constant, your air resistance remains constant. Okay, that's what the air resistance being proportional to speed actually means. Okay, so just make use of these two facts. We apply to an object that's falling with air resistance. Okay, the first part that I want to consider is where the object is dropped from rest. Okay, this one is actually the case where your object is dropped.
Wait, the second point is air resistance is not proportional to speed, is it?
Air resistance is proportional to speed.
Proportional to speed.
Wait, let me just... Proportional to speed. This symbol here is proportionality sign.
Yeah.
Okay, it's not the cross sign. Okay, this symbol here is referring to proportional. Just write in black.
So the larger the speed, yeah, makes sense. Okay.
It makes sense, right? Common sense will tell you the faster you go, the more resistance you encounter. the slower you go, the less resistance you encounter.
Yeah.
Okay,
Yeah. Makes sense,
so
yeah.
this one is something that's important to explain to you, something that falls with air resistance. Okay,
Mm.
so now with air resistance, you initially drop the object from rest. Your object would only have weight acting on it. Okay, this one what we'll say is that there is no air resistance. This one I can actually say that there is no air resistance R. No air resistance. Air resistance is not present because speed is 0 here because you're dropped from rest.
Yeah.
Okay. So the thing that I just want to draw your attention to is that F net here is equals to W, therefore acceleration is equals to G. Okay, this one is what we understand. Okay, then next we go to the point where it's midway. Okay. So let's just say your object is now started to move already. It's no longer from at the initial position. It's already started to move. So when it's already started to move, I know that the force that is acting on the object right now, there will be now two different forces. First one is the weight. Then the second one is the air resistance. Okay. So over in the initial part, because you will drop from rest, your V was 0. But here, your object, after it started to move, let's just say it's now at midway of its motion, you have speed now, so you're gonna have air resistance. Okay. So one main thing to take off from here is that there is now air resistance. There is now R because the object has speed. Okay. Now, here's where you start to need to wonder a bit about what is your net force. You see, right now, my forces is the weight W and air resistance R. Okay. So, knowing this fact, I can actually say that F net is actually now W minus R. Okay. Then after that, my net force is now W minus R. If you compare to before, my net force was just the weight. And when it's just the weight, my acceleration will be equal to the gravitational acceleration. So now, when the object has started to move, my net force is no longer just the weight because I have to take into account air resistance. My net force is now W minus R. Okay, so if you compare this with before it's F net equals to W, now it's F net equals to W minus R. It will be correct to say that my F net has decreased. Therefore, my acceleration would decrease. So far, so good with this logic. Okay, because now I have air resistance, my resultant force has actually decreased. If my resultant force has actually decreased, my acceleration would actually decrease too. So at this point here, my A is actually not equal to G. My A is actually supposed to be less than G. Okay, so far so good.
So that's in the midpoint.
Yes, this one is somewhere in the midpoint now. Okay, all right. Then after that, I give you another different case. Okay, now from here, I say that my acceleration has decreased because my acceleration dropped. Do you suppose that the object is still speeding up or slowing down?
Slowing down.
Okay, yeah, this is where the main important thing comes into play. It is actually still speeding up, but at a lesser rate. okay, at a lesser rate. Okay, now this is where things get a bit odd. You see, now I tell you the object is speeding up, but at a lesser rate. Okay, so one way of looking at this is by me drawing something here. Wait, let me just try and give you something. If I give you a range of speeds now, let's just say I draw it somewhere around your table here, and I draw it on this part here. If let's just say I tell you I have a certain speed, velocity, okay, my velocity went from 10 meter per second. You know, if let's just say for example, my velocity was originally 50 meters, maybe it's better if I start from 10. Right. It was 0 meter per second. Then after that, it became 10 meter per second. Then it became 15 meter per second. Then after that, it became 17 meter per second. Okay, so this one is velocity. If I ask you to consider a range of velocities for the velocity change of an object that is currently moving, like this, okay, this let's just say that this one is my object that is currently moving with a velocity of v. Okay, this one is the velocity of the object as it moves from 0 to 10 to 15 to 17. Now, when you look at it this way, am I correct to say that the speed is increasing?
Mm,
Speed is increasing. Okay,
mm,
it is speeding up. Okay, but is the speed increasing by a constant amount? Or
no.
is it increasing by increasing amount, reducing amount? You see, I can actually see a pattern here. From 0 to 10, maybe I use a different color. From 0 to 10, I'm actually having an increase of, okay, this color is not dark enough. I should probably use black. This one is increasing by 10. This one is increasing by 5.
Mm,
This one is increasing by 2. Okay, so you see, when I say speed is still increasing or still speeding up by a lesser rate, what I'm actually referring to is actually this. You see, my speed is actually still increasing. I'm still speeding up, but just that with each passing second, I'm actually not increasing in speed as much as before.
mm.
Okay, so this one I would say speed is increasing, but at a lesser rate. Okay, so this one is one thing. This one speed is increasing, but at a lesser.
Does this point relate to the your point saying at the same time edge resistance drag force increases with velocity, this causes resultant force to decrease further, causing acceleration to decrease further?
That one is the next motion that I will have to draw here. Okay,
Oh.
but now I'm just talking to you about the part where you're just midway first. All right, so this part you can understand, right? All right. Now, what if I try to now talk to you about the acceleration of this object? Let's just say, for example, this one. Okay, why is it in the first place that I mentioned that acceleration drops, but somehow I'm still speeding up? How does it somehow relate to you saying that your object still speeds up but at a lesser rate? Okay, this one has something to do with this. Let's just say, for example, this one I tell you is t equals to 0. This one is t equals to 1. This one is t equals to 2. And then this one is t equals to 3. Okay. So if I go from 0 to 1, this one could be a case where my acceleration is 10 meter per second squared. when you see acceleration 10 meter per second square, it actually means to you that each second your speed changes by 10 meter per second. That's why you see when I go from 0 to 1, my speed suddenly increased by 10. Now for the case where I go from t equals to 1 to t equals to 2, this one could be a case where my acceleration is actually 5 meter per second squared. This tells me that with each second that has passed, my speed increased by 5 meter per second only. Okay. Then if I go from t2 equals to 2 to t equals to 3, this one could be a case where my acceleration is 3 meter per second squared, which tells me, sorry, not 3, 2, 2, sorry.
Which tells you it increases but at a lower magnitude.
Yeah, correct. So you see, if I look at the diagram that the wordings that I've just written here, A is 10, A is 5, A is 2. If I just look at this one alone, in this particular direction, going down, it is correct to say that my acceleration is decreasing, isn't it? All right. But you see here, my acceleration decreases, but my speed is increasing at a lesser rate. So now you see, does this now make sense to you when I say this? Because my F net drops, my acceleration drops. Yes, correct. But my acceleration drops doesn't mean that I am slowing down. I'm actually still speeding up, just that it is at a lesser rate.
Because you're affected by air resistance.
Yes, because you're affected by air resistance. Because air resistance is the thing that causes your your net force to drop. It in turn causes your acceleration to drop. Okay. All right. So this one is okay. All right, then
because my net force is my weight, right?
Sorry.
Because my net force is my weight, which is g.
Yes, if my net force is just the weight, then my A is just equals to G. But
That's
then now
fine.
if
Therefore, it causes my net force to drop. Therefore, like
my acceleration will be less, no? My
yeah.
net force drop, my acceleration obviously drop, ma. Because
Mm.
now my net force is less than the weight already. Obviously, my acceleration would not be as much, no? It will be less than G, no? Okay. Right. Okay. So next part of the motion. Let's just say you are further midway, further downwards. Okay, maybe I just say further down, lah. This one, let's just say you're further down. If you're further down, again, I still have my object where I have my weight W and my, cannot, maybe this one I need to draw it a bit further down because it's blocking the diagram. So another one would be where you are talking about the object being further down. So my object is here. I again still have my weight W, and again I still have my air resistance, and I'm still actually moving downwards. Okay, so say for example right now, what can I say about my air resistance? My R is larger because speed has increased. Because speed is higher now. Okay, remember the last stage here, I mentioned that your object was still speeding up, but at a lesser rate. So because I'm still speeding up, at this point here, my speed is larger than before. Okay, so logically my air resistance will be larger. Okay, now here, if I look at it this way, R remains constant, but R increase. Therefore, my F net would actually drop further. This one, my F net again will drop further. And then my A will also drop further. Okay, make sense? So my R is now bigger than before. My W is constant, so my Fnet will drop even further. Okay, so if it helps you to somehow understand better by having values, maybe I tell you that W here is 100 Newton. My R here is say 20 Newton, while my W here is 100 Newton. So my Fnet here is going to be 80 Newton. But now when my object is moved further, my air resistance increase. So it could be that now my weight is still maintaining at 100 Newton. My R is now maybe 40 Newton. So my Fnet is going to be 100 minus 40, giving me 60 Newton. Okay. So let's just say I want to give you some values to relate to the diagram to the wordings that I've just written for you. I could say that maybe your V here was originally 10 meter per second, but now this one becomes 15 meter per second. Okay, so this is what you're seeing right here. You are having an increase in speed, although you have a reduction in net force, although you have a reduction in acceleration. Okay, so the thing that you just want to see here is this. You see, I know that if I keep dropping down, the weight remains constant, but my air resistance will keep increasing. So it is correct to say that my air resistance will keep increasing, but you eventually increase up to a certain value only. You see, right now, in my current case, weight was 100 Newton, air resistance is 40 Newton. I know that if I drop further down, my air resistance will keep increasing as I increase in speed. Okay, so the air resistance will actually only increase up to a point where it's equals to your weight. Okay, so when it increases all the way until the point where it's equal to your weight, you actually would stop speeding up. All right, so this is where I need to kind of draw it somewhere. Okay, this one I have to erase the things that I just wrote here so that it's easier for you to see. Okay, the last stage will be here. This one is the stage where you reach terminal velocity. Okay, this one I'll just write it here. This one is where you reach a stage called terminal velocity. Now, at terminal velocity, what will happen is that your object is here. You have your weight W, and then you have your air resistance R, and then you again still have your velocity V. Okay, so what I will say here is that at this point, your R continue increasing your R continued increasing until it is equal to W, okay, equal to the weight. So if just now it was mentioned to you that your weight was 100 Newton, your air resistance now increases up to 100 Newton too. Now from here, I can then make a conclusion saying this. My Fnet would actually now be 0. Okay? Because originally Fnet was supposed to be W minus R. But if now the R is equal and opposite to my weight, my Fnet is 0. Okay? So my Fnet is 0, my A will be 0, and then what I can also say here is that because my acceleration is 0, what can I say about my velocity? Velocity
Constant.
becomes constant. Okay, so it reaches when my velocity becomes constant, what we'll say here is that your object has reached
Terminal
a
velocity.
maximum speed called terminal velocity. Okay, this is what terminal velocity actually is. All right. So whatever I just wrote here is actually the same. It's actually what I'm trying to explain on the screen. All right. So if you compare to the case without air resistance just now, like I mentioned to you, the key takeoff point was that without air resistance, my object will actually speed up indefinitely. It will actually keep on increasing in speed up to infinity, so long as there's space for my object to fall down, right? But when you have air resistance, your object actually doesn't continue to speed up indefinitely. It will eventually reach a maximum speed called terminal velocity. Okay, so in your case here, you actually will need to know some of the graphs that are specific to an object that's falling with terminal velocity. Okay, so before I go to that, let's just review a little what I just wrote here, just to uh, refresh your memory a little on all the explanations I've done. Now, with air resistance, a falling object will increase to a maximum, or falling object's velocity will increase to a maximum constant value called terminal velocity. So as the object initially falls from rest, its acceleration starts off with the value g because the F net is equals to W. But as your ball starts to move, it starts to encounter air resistance or drag force. Here, your net force becomes Fw minus R. And then, as a result of that, your resultant force has decreased, so does your acceleration. All right. But your object will still continue to accelerate, but with a lower magnitude, while at the same time the velocity increases but at a smaller magnitude. This is what we mean by increasing at a lesser rate. Okay, so at the same time, because you're having your speed increasing, your velocity increasing with smaller magnitude, your drag force or air resistance will actually still increase, because what you're essentially doing was that you're moving from 10 to 15 and then to 17. It is still considered an increase, but just that each time the increase is less. Okay, so your air resistance continue to increase. This in turn causes your resultant force to decrease further, causing your acceleration to decrease even further. Meaning to say it could be originally 5 meter per second, but then suddenly now it dropped to 2 meter per second. Okay, so F net equals W minus R decreases, thus A decreases, while at the same time your velocity increases but at a lesser magnitude than before. So your process will actually keep on continuing until such a point where you reach a limit. Here, what we'll say is that your air resistance will actually increase until it's equal opposite to your weight. At this point, your resultant force has actually dropped to 0, and your velocity has actually increased to become constant. Okay, so at this point, your body no longer accelerates and it actually continues at constant terminal velocity. So in terms of the graph that you expect to see, it basically looks something like this. Okay, this one I'll just erase it off. Okay, so if I just look at the velocity time graph, this one, you will notice that my graph, my velocity is increasing here, and then suddenly it becomes constant.
As you reach terminal velocity.
Yes, because this one here is actually your, like this part here is actually your terminal velocity. This one, let's just say your terminal velocity is Vt lah. Okay, so here, over this side, you have reached constant velocity. Okay, But what about the part before that? Okay, you see here, your velocity is actually increasing, but each time it seems to be increasing less and less. You see, the gradient is actually becoming less and less and less, right? Isn't it? And also, you know that gradient or your velocity time graph is actually your acceleration. You actually can see here, gradient drops, acceleration is dropping. And then this one is gradient 0, acceleration is 0. Acceleration is 0. Okay, so here gradient drop, acceleration is dropping, but you're still speeding up. Okay, so this one you're speeding up, but at lesser rate. Okay, so this is what is actually happening now in terms of the graph. All right, you can see that your velocity is increasing, but each time is actually getting less and less until such a point it suddenly stops increasing. You reach what we call terminal velocity here. Okay, so this one is something that you can see. This is the most important graph a lot of times. You see, this velocity time graph compared to the velocity time graph without air resistance, it looks kind of different, right? This one here tells you that your velocity keeps increasing in a straight line all the way to infinity. But the other one with air resistance tells you that you will not actually keep on increasing. You increase less and less each time until you reach a maximum. Okay, that is terminal velocity. Okay, now, then after that, some other less common graphs would be probably where they ask you to talk about the acceleration time graph. This one is on the left-hand side. So let's just say you have an acceleration time graph. Remember just now, it was mentioned that your acceleration starts with g, and then it will just keep on decreasing to 0. So if it keeps on decreasing to 0, this is what it looks like. Okay, it will decrease all the way to 0. Okay, now in terms of the displacement, this one is another different understanding to it. If you look at your graph here, this part here is where you have velocity increasing, so your gradient is actually increasing. This part here is where your velocity is constant, so your gradient is constant. You know, maybe better use a different color here not to confuse you. Oh, okay, I'll use this one. This one velocity was constant, so gradient is constant. Okay, because you see that time I mentioned to you, for velocity is defined as rate of change of displacement. The value of your velocity is equal to the gradient of your displacement time graph. So you look at your velocity time graph, this one, you can see that your value of velocity is becoming more and more positive, right? Or in other words, it's increasing. So your gradient obviously will become more and more positive, or it is increasing. Okay, but this part here, where you reach terminal velocity, this part is where your velocity value becomes constant. So your gradient must become constant too. You see, this one is constant gradient, it's a straight line. Okay? Right? So this one is something that you can somehow appreciate. Alright? It seems like there's a lot of things to take in, right? That's why I have to kind of like do it step by step, just so you can actually appreciate it. Okay, there's a very big difference between something without air resistance and something with air resistance. Okay, so far so good with this. Okay, now something reaching terminal velocity doesn't only occur for something that falls through the air. It can also occur for something that is falling through a liquid. Okay, I think this one I wrote it towards the late end part. If you're okay with this, I just clear off the screen first. Is it okay? All right.
Yeah.
So I'll just clear the screen. Right. Now, the last two statements here, we mentioned to you that for a body that falls through the air, normally we don't consider upthrust because the weight of air displaced is negligible. Remember in one of the previous chapters, we mentioned something about upthrust is actually equal to the weight of liquid displaced or weight of fluid displaced, but we normally just don't bother about for air or gases because the weight is very little. So now, if you have something that falls through water or any other liquid, you need to consider upthrust. Okay, so the object will eventually reach terminal velocity 2. Okay, so let's just say, for example, I have something or the same object, the same ball, okay, the same ball that I was just dropping through the air, but this time I go and drop it inside water. So I let it start from rest inside the water. You drop down to the bottom of the ocean or lake or whatever is being dropped to. But the thing that is of interest to you is that when it drops down, it will eventually reach terminal velocity 2. Okay, so it will actually reach VT eventually. Okay, same like when it was in the air. So if that's say this one, I tell you this one is say water now. Okay, so this one, the ball will reach terminal velocity eventually. Just write this on, the ball will reach terminal velocity 2. Okay, but the only difference now is that when it comes to the forces that you consider, your forces, you have to just take into account another additional force. You again have weight, you again have you again have viscous drag. Okay, not air resistance now, but viscous drag or drag force, if you would. And you also have upthrust. Okay, so this is the one that you need to consider. Now, at terminal velocity, what do you suppose would be the expression for your forces? Now, one of the things you remember about terminal velocity just now was that F net must be equal to
UR equals to 0.
sorry,
UR equals to 0.
U UR is equals to UR is equals to 0. Okay, now I have three forces here. W, R, and U. Is there an equation I can form from these three?
MG. What? U.
Yeah. Okay, I have U.
I feel like it's the equation we did before. Is it the
Yeah. Right now, if I ask you
is it
to
the constant as a is it the kinematics equation?
no. This one is not talking about kinematics equation. This one is just asking you to consider these three forces. Okay, let me
UR.
just try to redo this for you. Before this, if I have weight W and air resistance R, and I tell you that this one is my motion,
F
F
net
net
equals to
will
F net
be W
equals
minus R, right?
to
Correct? Right. But what
W
about,
minus U minus R. W
yeah,
equals to U minus R.
W equals to U, W minus U minus R. Yeah, okay. So back to this one, at terminal velocity, I know F net is 0. This one, W equals to R, right? Okay. So I'm trying to do the same thing here for you. you are correct in saying that your F net would actually be W minus U minus R. So let me just write it properly for you. This one, you have W, this one you have R, this one you have U. So by right, your F net would be W minus U minus R. Okay, yeah, again, not forgetting this is the direction of your motion. So your F net is W minus U minus R, but at terminal velocity, your F net would actually be 0. So here, I can actually say that W must be equals to U plus R, right? Which is basically, in another way, this one is essentially saying that downward force is equals to upward force. Okay? So this is how you would apply it for something else that moves with terminal velocity.